So let me talk a little bit about low energy buildings with energy storage, because that's actually what my very first project in Malaysia had to do with that, and we are still doing projects like that, where we basically try to help the grid, so it doesn't have to, so we don't have all this energy demand during the peak demand time during the day. So here's a little, this is from the website, so I think the IEA website, you can read that on your own, and you will also get the slides, I believe. So this is the structure of the presentation. I'll basically take you through some of the energy efficient case studies that we have done here in Malaysia with local energy storage. So I'll talk about the zero energy office building. I'll talk about the ST Diamond building. I'll talk about the Pyramid factory in the forest. So that's the photo you see there on the right, where we went to visit. And I'll talk about the Living Lab, which is a project that's only been officially launched later this month. So all these projects are basically highly energy efficient buildings, and where we also have some kind of thermal storage, which of course makes them grid interactive ready. As we have heard, that buildings have to play a key role in this flexibility once we go into this much more renewable energy sources that fluctuate. So let me jump straight to it. This is the zero energy office building in Malaysia. Now it's called the Geo building. This is the measured energy consumption. So this is kilowatt hours per square meter per year. So you can see it's actually really very low, the green bar here, compared to what a normal office building uses. So I could talk a whole day about the energy efficiency we did on this building, but for this presentation, I'll just mostly focus on this storage aspect of it. And this building actually won the ASEAN Energy Award in 2020 in the zero energy building category. And it was actually a co-winner or joint winner with the SDE4 building at the NUS University in Singapore, which has a similar measured energy consumption, but has a bit more solar. So the main energy design concepts for this building was basically to really push energy efficiency as hard as we could and get the building to zero energy. So we had a lot of building integrated PV, 4 different types of that on the building, as you can see from these photos, on the big roof, but also on the car park roof here and on the embedded in the atrium. We then practiced this principle of load shifting. So basically trying to run the chiller only at night when there's a low demand on the national grid, and then in the daytime we would already have done our cooling, because that would be stored in the building, and therefore we wouldn't have to consume energy. We might even be able to export electricity, because all this PV is connected to the grid. So this is the demand curve in Peninsular Malaysia, and you can see peaks here around noon or in the slight afternoon, where it's hottest, where aircon loads are very high, and it's lowest in the night. So the idea was that we only run the chiller, which is of course a major consumer in this building at night. So we buy electricity from the grid, we store it in thermal storage, and then we sell electricity back to the grid during the day using solar photovoltaics. So here you can see all the solar systems, and here are some of those energy storage systems that we used. I'll go into more details. So this is a schematic of the cooling system with the 2 cooling storages. So I'll just highlight them like this. So the first cooling storage is a so-called phase change material tank, or PCM. And you can actually buy these kind of phase change material tanks or materials with any melting point or any melting point that you want. So in this case, we decided for a 10-degree sort of salt solution that freezes like ice, except that it happens at 10 degrees. And the reason we did that is that it meant we could still use back the same chiller, because we didn't have to go to like an ice storage facility, which requires a different chiller and to use glycol in some of the circuits. And then the other storage is a floor slab system. So basically, I'll talk about that, but basically cooling down the structure of the building, which typically in Malaysia is built from reinforced concrete. Another innovation, if you go back here, again, is that at night, because the building was designed for this chiller only to run at night. So instead of installing a cooling tower, we actually designed it with a so-called river roof. So we had this manifold pipe on the top of the PV roof and just let this water run across the solar cells, as you can see on this one. And therefore, and then ejecting the heat to the night sky. So most of the heat was released to the sky through radiation, and a little bit was through conduction and evaporation, but very little evaporation because the relative humidity is quite high at night because the temperatures are lower. So it actually also meant that the makeup water for this building was very low because we virtually didn't evaporate any water because we just emitted most of the heat to the cool night sky. And the night sky is actually, if you look straight up, if you take one of these temperature guns that can measure surfaces, you can try it for yourself. A lot of people are surprised to measure that it's about 10 degrees, maybe 15 degrees. It depends a lot on the cloud cover. I have measured down to -22 degrees on a clear day without clouds. So you can actually have a significant heat radiation to the night sky at night. And then if we go to the thermal storages, so we built this tank with all these ice packs inside with this phase change material tank. So we had 580 kilowatt hours of storage capacity there. The ice packs only start to charge when you subcool them a bit, so we needed 7-degree water to cool them. And then we basically run water through this tank at night when the chiller runs, and then in the day, so all the salt solutions freezes to ice, so to speak. So come morning, we can switch off the chiller, and then in the daytime we only have to run a little circulation pump to run water through this tank, and then the ice packs melt, and we get this kind of 10-degree water out of the tank, and that is good enough to do some dehumidification, so we can run this water into the air handling units and the fan coil units. And the other thermal storage was the floor slab cooling. So basically laying out these pipes spaced about 200 or 300 millimeters from each other, and sort of embedded in the concrete pipe. So here you can see it's laid on top of the RC slab, and then after this we poured a 75 millimeter screed layer on top. So they're basically inside the concrete slab and would give cooling both up and down, mostly down actually, because in the upward direction there would be a carpet, which of course insulates a bit, whereas in the downward position there would be no carpet, it would be an exposed ceiling, and cold air drops, right? So they would cool down the air around the ceiling, which would drop down through buoyancy, and then be replaced by hot air. So you would have this kind of convection cell happening automatically. So most of the cooling is actually coming from the ceiling for this system. And this is basically running at night only. So just like for the phase change material tank, we just cool down the the slabs to about 21 degrees at night. And then that cooling is released passively during the daytime, or rather they absorb the heat in the building. So when people enter the building, when some sunlight enters, when heat from the lighting and printers and so on goes into the space, it's absorbed into the into this big thermal mass, and then the temperature of that floor slab will actually increase about 1 degree during the day, and then come nighttime we cool it down again by 1 degree. So it's actually a very stable system. And here you can see how they are laid. The green ones are the floor pipes. We stopped them short a bit from the facade because we didn't want to lose too much cooling to the outside through the building facade. And the advantage of this kind of floor cooling system is that it increases the chiller efficiency, because the lift of the chiller is significantly reduced, in this case by about 13 degrees, because instead of supplying a 6-degree water, chilled water, which is very standard for most chillers, 6 or maybe 7 degree, now we only had to supply 19-degree water. So that is a lowering of the lift of 13 degrees. And therefore the chiller efficiency, this is the Carnot efficiency on the right, which is the theoretical maximum efficiency of chillers, basically doubles, a bit more than doubles. So therefore you can get you can get twice as much cooling for the same energy by doing this kind of high temperature cooling for these kind of thermally activated building systems. The other advantage is on your energy bill, because this system is running at night. So if you have a peak off-peak tariff where you can draw on the off-peak, that means you can do all your cooling for the cheaper electricity rate and also save money there. We installed the same system in the ST Diamond building, which is also an office building here in Malaysia. And for this particular building, we were lucky to do some detailed measurements. I think about 2 years into the operation of the building, where they had a shift of the facility management team, and where they basically took the building off the automatic control, and the whole slab cooling system went a bit haywire, which gave some very interesting results, because the normal operation is here in the middle, where it says typical week, where you can see that the ceiling temperature, which is the red curve, is basically going up and down like this. So in the morning it comes down to 21.5 degrees or so, and then it increases during the day, and then reaches a maximum temperature of about 23 degrees. And then that's a bit cooler than the room temperature, which is a black curve, as you can see here. And crucially, everyone always asks, so does this mean that you have compensation in the building when you cool down the surfaces? But you can see the dew point temperature measured in the space is down here, about 17 degrees. So as long as the ceiling temperature does not drop below the dew point temperature, then there's no compensation happening. But the week before, where they decide to override the operation, and where instead of feeding 19-degree water into the floor slab cooling system, they took the chilled water that's meant to go to the air handling unit, about 7-degree water, and then you can see you've got a big drop in the ceiling temperature, and we dropped below the dew point temperature, and that means water started to condense on the ceilings, and they were sort of raining indoors. So this is of course not the right way to operate it. Then they put it back to automatic, and then I think there was a lot of complaints maybe, then they switched off the system completely. So the next 3 weeks over here, it's not switched on, and the building only operates on the air conditioning system. But of course that air conditioning system was only dimensioned to cater for about 60% of the load, because 40% of the cooling comes from this floor slab cooling system. So therefore you can see the black temperature, which is the room temperature, is higher than this typical week. So therefore it was a bit warm for those days. So actually we were lucky to capture these 3 different modes of operation for floor slab cooling systems, which are not very common out in this part of the world. Another building that we have successfully used this thermal storage system is for this factory. It's up at Penang. It is also a very efficient factory and has won a lot of awards. And 1/3 of the cooling is done this way, so basically feeding these pipes into this concrete floor. So for this building, we laid about 65 kilometers of this cooling system, and it basically, once it's embedded in the concrete, it can last for 100 years. So unless you drill through the concrete floor and puncture the pipe, there should be no problem maintenance-wise. And even if you do drill into the floor, you can hack down and repair it if need be. Or you can switch off that loop on these manifold pipes that is affected. And here's an illustration of the floor slab cooling system, how it links to the chillers. So for this building, we had a specific chiller for the slab cooling system. And I can also mention that was actually also the intention for the original project, the Zero Energy Office, but at that time, these kind of chillers were not available. So that was one of the reasons why we didn't, the cooling system didn't become as efficient as we had hoped, or that we knew was theoretically possible, but it was not practically possible at the time. But for the upcoming chiller retrofit, hopefully we can get it right. Then let me just finish off with this project. This is the ongoing one, which is being launched later this week. And this is a living lab teaching facility at one of the universities here in Malaysia. And here we again have, we push energy efficiency. It's also a zero energy building. In fact, it's actually going to be a plus energy building, so it produces more electricity than it consumes. And for this building, we have 2 energy storages. This time it's a thermal one and an electric storage. And since it's a university, it's built with some extra features, which means the students can actually monitor and control and try to optimize this, how to operate this building. And it can also be connected to the grid. It is connected to the grid, and it can have this standalone capability. So therefore, it's actually quite an interesting building, and I'm sure there'll be a lot of research on this. So the thermal storage tank is basically some big water tanks, and we designed very carefully these manifolds. So we have the right, we sort of slow down the water speed, so we get a very good thermal stratification in the tanks. And also the way we loop it, we have some manually valve settings that can be adjusted, and this can be done by the students, where they can also explore whether coupling these tanks in series on parallel is the more optimal way for this thermal storage. And then for the electric storage, it's basically a battery. And here you can see how it's connected to the inverters and controllers and the grid and so on. Some of the simulations we've done here, and this was a little bit on an earlier stage, so we actually have more solar panels now than for this graph. But basically, here we are trying to prioritize the electric storage. So the electric storage is the green one, and this is seen over a 2-week period. So what you can see is for this building, which is used during the weekdays, Monday, Tuesday, Wednesday, and so on. So what happens in the weekend where it's not in use, that both the electric storage and the thermal storage, which is the purple, they basically are fully charged up. And then during the week, to basically meet the cooling load and the lighting load and so on, then they are slowly depleted. The thermal storage here is depleted immediately, and then it's the electric storage that is drawn upon mostly. So we did something similar where we prioritized the thermal storage, because in this case the thermal storage is much more environmentally friendly than the electric one. It's basically water, so there's no environmental impact of having a water tank, or almost none. So here you can see the thermal storage is first charged, so it's charged up at the end of every day, and then it's depleted in the early morning hours when the sun or when the building starts operating, but there's not enough power from the grid, from the sun to operate the chiller yet. So this can be optimized, and it will be interesting to follow this project, and also with the university staff and students to see this optimization and the grid interaction. Oh, there's a spelling mistake here. I can see. I should say grid interaction. Yep. So basically, I just finished with this slide, which was presented this morning by Pauline Henriot, because she basically said that this demand-side flexibility is a key to reaching net zero, and the buildings are going to play a major part. So I think some of these case studies and these kind of technologies that we have shown here are part of the solution. So I would say these buildings are sort of grid interactive or sort of ready, but the whole optimization with the grid is not something we've looked at too much, but we know it's important, and we have sort of shown the way.